Welcome back, folks, to another exciting JLAM Bio video. Today, our focus in Chemistry 2 is on empirical and molecular formula. So what we're going to be giving you is we're going to be giving you percentage of elements in a compound or the grams of elements in a compound, and your job is to be able to determine the empirical and molecular formulas from that. We're also going to look at a process that is known as combustion analysis. You remember the combustion of a hydrocarbon plus oxygen yields carbon dioxide and water. So we're going to be able to analyze those particular molecules, we're going to analyze those particular chemical reactions in order to determine the empirical and molecular formula of our hydrocarbon starting out. So a lot going on in this video. Let's move forward. But before then, I'd like to thank my sponsor, Big K Diet Cola. I'm just going to try this out right now with my new microphone. Just a little chemistry ASMR. Ooh. You hear that? That's the sound of refreshing. Now I'm ready. Let's get started. By the end of this video, hopefully you will be able to perform combustion analysis to determine the empirical and molecular formula of a hydrocarbon. You should also be able to explain the steps on calculating empirical and molecular formula and calculate each, as well as the concept of calculating percent mass. So, our key vocabulary terms for today, again, empirical formula, molecular formula, and combustion analysis. So what's the key difference between the empirical and molecular formula? Well, the empirical formula of a compound is given in the lowest whole number ratio. So if we look on the right here, the empirical formula for glucose is CH2O. However, the molecular formula is the actual formula of the compound. That would be C6H12O6. So there's a key difference here between the empirical formula, lowest whole number ratios, and the molecular formula, the actual formula for the compound. Do keep in mind, though, in some instances that these can be the exact same thing. So we're going to go through and analyze how to go through this process and, well, go through the process. Let's move on. So in order to calculate the empirical formula, we have several steps that we're going to take a look at. Number one, we need to convert grams of each element into moles. And if we're given a percentage, we assume that those percentages are in grams. So for example, if we're given something that's like 66% this, 34% that, we just assume that it's 66 grams and 34 grams. Makes things a little bit easier on us. We divide all of the species by the smallest number of moles. So once you convert everything into moles, the smallest number of moles that exists, we divide each species by that number. Now, if we get whole numbers, great, we're done. But if not, we have to multiply by whole numbers, if necessary, to eliminate any decimals in your numbers. So for example, if we get something that's a half, well, we have to multiply all of everything by 2 in order to get it to become a whole number. And then lastly, the numbers at the end are your subscripts. So then you can just write out your empirical formula that way. Let's do a practice problem to check our work. Determine the empirical formula of the compound with the following mass percents: 58.5% C, 4.91% H, 19.5% O, and 17.1% N. So we're given percentages. The first thing we need to do is to write these in grams. So 58 grams of carbon, 4.91 grams of hydrogen, grams of oxygen. Our next step is to convert each one of these into moles, so we're going to use the molar mass. And I find that on the periodic table. What's nice is a lot of these are pretty easy to remember. We plug these into our calculator and solve. So if we take a look at our values here, again, we need to divide by the smallest number here. So we're going to divide all 4 of these by 1.21. Now you can take a little bit of liberty in here in doing some rounding. So for example, we know that this is 1. This number here is close enough in order to be 1, so we'll call it 1. This number here is 4, and this is 4. So those are our coefficients. If they're whole numbers, we don't have to multiply by anything. So our empirical formula here is C4H4ON. All right, and we're done. Pretty straightforward on that concept. Just make sure you follow the steps one at a time. Now, in order to calculate the molecular formula, we need to compare the molar mass of the empirical formula to that of the molecular formula. So if it's asking you to calculate a molecular formula, the molar mass of the compound should be given to you. You'll need to find the molar mass of the empirical formula by doing some basic calculations, just like you would any molar mass. You're going to divide the molar mass of the molecular by the empirical, and what you should get is a whole number. Once you get that whole number, you're going to multiply each subscript by the number described in step number 2. Then you will get the molecular formula. Awesome! Let's take a look at a practice problem just to see if we know what we're doing. So in this particular problem, a 2-gram sample of a liquid that contains only hydrogen and carbon is found to be 0.2874 grams of hydrogen. If the molar mass is around 71 grams per mole, what is the empirical and molecular formula? So before we do our molecular formula calculation, we are going to need to complete another empirical formula. Now in this instance, we're told that we are given a 2-gram sample and that 0.2874 grams of that is hydrogen. The sample only contains hydrogen and carbon, so we can subtract 0.2874 from 2 in order to get the grams of hydrogen that are present in the sample. So we end up with 1.7126 grams of carbon. So we need to do our empirical formula calculation first. So let's get both of these down here. And we're going to, again, convert both of these to moles using the molar masses. We divide by the smallest number that's there. 0.1427 is less than 0.2846, so we're going to divide by that. And there's our ratio. Okay. So again, our empirical formula is going to be CH2. Now the molar mass is around 71 grams per mole, so we need to find the molar mass of our empirical formula. So C and 2 H's is going to give us 14.01. We take our molecular molar mass, divide by our empirical molar mass, and that should give us close to a whole number, which is right around 5. So my formula now, I just need to take 5 and multiply all of my subscripts by that. So it's C5H12. All right? And you can go back and double check that as well. You can double check the molar mass of this compound here and see if it is close to 71. If it is, you know you did your answer correctly. All right? So let's move on to the next problem. Now, when we talk about combustion analysis, we get carbon dioxide and H2O as our products. Based on this information, we can do some molar conversions to be able to determine how much carbon we get and how much hydrogen we get, utilizing a little bit of stoichiometry trickery, so to speak. The rest then would be oxygen. We can then do empirical and molecular formula calculations. So if you look over here on the right, we can actually convert moles of CO2 to moles of carbon, because based on the coefficient, there is 1 mole of carbon in 1 mole of CO2, because it's C1O2. For hydrogen, though, it's a little bit different. There are 2 moles of hydrogen for every 1 mole of water, so we have to do a little bit more math with that. And then we can do a little bit of extra work to figure out what oxygen is left over. All right? So let's go through, let's do some math, and figure out where to go from there. All right? So let's take a look at this sample combustion analysis practice problem. A 1.5 gram sample of hydrocarbon undergoes complete combustion to produce 4.4 grams of carbon dioxide and 2.70 grams of water. What is the empirical formula of this compound? So remember, in order to figure out the empirical formula of the compound, we need to determine how many grams of carbon dioxide we started with and grams of H we started with. So in order to calculate the empirical formula of this compound, we need to know how much carbon and hydrogen are produced. Now, fortunately, here is the only source of carbon in a combustion reaction. Okay, it's the only part at the end that has carbon. This is the only part that has hydrogen in it. Oxygen's a little bit tricky. We'll get to oxygen here in just a minute. So let's figure out how many grams of carbon are in 4.40 grams of carbon dioxide. So we're going to do a little bit of dimensional analysis. Grams of CO2. And we're going to go grams to moles. Okay, just like we always do. Now for every 1 mole of CO2, because the subscript is 1 for carbon, we get 1 mole of carbon. And 1 mole of carbon is 12.01 grams. So we'll know how many grams of carbon we have in our sample. We do the same thing for water to figure out hydrogen. Get molar mass of water there. Now for every 1 mole of water, because again of the coefficient here, of the subscript, we have 2 moles of hydrogen. Now this is not a Brinkelhoff moment here, so 1.01 grams of hydrogen. So when we go through and calculate these, we're going to figure out how many grams of carbon and how many grams of hydrogen we have from our reactants. So if we take a look here, we have 1.2 grams of carbon and 0.30 grams of hydrogen. Now what's nice about this is when we add these together, we get 1.50 grams. That tells us that there is no oxygen in the compound because 1.2 grams of carbon are in my products and 3 grams of hydrogen are in my products. The law of conservation of mass says that whatever I put into a chemical reaction, I must get back out of it. So because I get 1.50 grams out of this, there is no oxygen. If we got something like, let's say, 1.20 grams, then we would have 0.30 grams of oxygen, okay? Because 1.20 grams is carbon and hydrogen, so the rest must be oxygen. But because we don't have this, we don't have to worry about it. So we're going to use 1.20 grams of carbon and 0.30 grams of hydrogen in our empirical formula calculation. So now we're going to utilize these numbers in our empirical formula calculation. So we're going to start with 1.20 grams of carbon, 0.30 grams of hydrogen, and again, just like last time, convert those to moles. Lowest number is 0.10. We're going to divide by that. So we're going to get 1 and 3. So our formula is going to be CH3, at least our empirical formula. Didn't ask for molecular, so we're not going to worry about it. All right, so again, just practice with some of these problems. We will go through some of them in class, especially some of the combustion analysis. I know that's a little bit more work, but I know you guys will do just fine moving forward. Let's keep going. So hopefully you got everything you needed out of this video. You will be able to perform combustion analysis to determine the empirical and molecular formula of a hydrocarbon. You should also be able to explain steps on calculating empirical and molecular formulas and to be able to calculate each and to calculate percent mass. Hopefully you guys got a lot out of this video. Again, my name's Jay Lamb Bio. Make sure you like, subscribe, shop merch, and we will see you guys next time. Have a great day, guys. We will talk to you later. Peace.